This video is about sea level changes. Here you can see an image, find it on the internet by NOAA. It shows that in the recent glacial maximum, 22,000 years ago, sea levels were about 125 meters below where they are today. And sea levels stabilized about 6,000 years ago here, but before that there were dramatic events in mankind history when sea levels were rising very rapidly, having horrible consequences sometimes for people. People were living in the North Sea, where we now have Dogger's Bank, I think it's called so also in English. I can magnify this graph. Here it's magnified, and you can see this point. That is 4,000 years ago. And this is the Linux tool. It's a Linux image processing program, and here you can see the coordinates. So 0, well, this point is minus 10 meters, that's 324. Minus 20 meters is 364, means 40 pixels for 10 meters. So if I go from today and 4,000 years back, today is 285, 4,000 years back is 288. So that is 3 pixels, or maybe 289 would be 4 pixels. So about 1 meter in 4,000 years. That has been the latest sea level rise. 1 meter in 4,000 years, that is 0.25 millimeters per year. But note that the measured data points go up and down a little bit. So this is probably not quite stable, because probably temperature has varied a little bit up and down through the history, and there are uncertainties in the data points also. Today we know that temperature is rising by something like 0.13 degrees per decade. That's the order. The second decimal is uncertain, or at least I don't know it for sure. What you see here is the satellite measurements from 1993 to 2012, and they have extracted a rate of change that is 3.2 millimeters per year. And that's much more than the 0.25 we have seen over several thousand years. Here is a graph over what has happened from 1900 to 2020. And I think this is what is generally believed today. This is from Columbia University, and last modified year 2020. Now, there are tide gorge measurements back through the 17th century and up to today. This one is from the Netherlands, and I can select other ones, global stations, and let's say Denmark. And it's also a straight line from 1890. So many of these tide gauge data are straight lines. They don't show the curvature that we see that is attributed to global heating. Now, what this means is obscure, and I feel very uncertain about what to say about it. So I have started a little investigation on this subject. Measurements of tide gauges are available at this permanent service for mean sea level. And referencing recommendation, I want to include that. And here you can read what they want. And the data was downloaded a couple of days ago on May 3, 2021. The retrieved date. I don't know how to find this better. Anyway, data is here, and I can click here and go for Europe, and let's say this place, plots, and here you see the raw data every month over this period of time. And this is smooth for yearly mean values. I have downloaded data from this site to make my own study on what they are saying. I have looked through all the tide gauge data files. There were something like 2,300 or so, and selected those that have a good completeness in the range 1960 to 2015. Many tide gauges have very short time spans and a lot of missing data. But I look for a completeness over 90% and a time span that includes 1960 to 2015. And this is the data of those that I have selected, and I have them in a text file on the computer. And it looks like this when I step, and you can see completeness ranges fairly high. I have written a simple program that reads all those files that I have selected and displays them one by one, like this. The strong white points are from 1960 to 2021. The red line is a slope that I thought would be reasonably appropriate for the entire time period. I don't remember exactly, something like 1.9 or 1.5 millimeters per year. And it's obvious that variations occur. Some are curved, some are sloping upwards, and some sloping downwards. But a large number fit to the line, more or less. I will allow it just go through all the stations, and you have your names here. So, with the appropriate tool, you can step through the video and look at these individual raw data plots. And some of them are obviously not useful. I will show that on the PMSL site after having run through this. And it's clear some have bending upwards, as expected from the data from NOAA, but some behave different from that, and a large number don't show the curvature that is expected. And on some graph you see magenta points. Those are the points that are flagged as uncertain in the database, one way or the other. And of course there are also missing points, and at those years or months rather, the trend line, the red line, is missing. And here, for example, you saw one that was starting to steep. And that was all of them. On the PMSL site here, I can show some of the data points I have not included. For example, Fukushima. And you can see here a steady straight line, and suddenly there was a big earthquake. And note, this is more than 1 meter. So something happened before the earthquake. I don't remember which year it was, but I don't have enough information, and really this is not something to worry about. And also neighboring stations, that was Fukushima. I can take another one here, and you can see at the date of the earthquake there is a big jump, and the islands outside also has a big jump. And something is happening gradually before the earthquake. And I guess long tide gorge series like this could tell scientists that something is moving with an increasing speed. That will have an end, maybe a dramatic, like it happened here. But I have not excluded a lot of stations that are most probably not reasonable to include in this study. So I will do that by processing the data and compare the files to each other and find some of them that don't seem realistic to include. When clicking on a station, I can have the plots, but I can also look at metadata, and it says warning, quality flag exists, please read the documentation. And I have to click elsewhere to see the documentation. The identity is 635. And then I go here, and here I can read a massive earthquake, magnitude 9.0. So When I look at the data files and find things that look odd, I will check this and remove what should be removed and retain the rest, even if it looks a little bit odd. I can step through the files one by one, like this, and I will do so and stop at the ones that look very suspicious. This one, number 15, is Kushimoto, and this looks as expected more or less. It's flat here, and then it bends and goes much steeper. And this is right between 1960 and 2020, so it's about 1980 or 1990. So this one behaves like expected from the graphs on the global sea level. Here is another one with the opposite behavior, more or less. It goes down here and then it's flat. But probably this is an error. The station is number 18. This is a place near Trondheim in Norway, Heimsjö, I guess. And looking at it, it looks reasonable with the open sea near. And we see the same phenomenon here. But looking here, you can see there is a lot of missing data points. And as you can see here, all the data from here and up to here. Sorry, there are many red magenta dots in this region before 1960. But I can read station documentation. Previously, data from 1958 and before was flagged suspect. So the flags have been removed. But I find this probably not compatible with the majority of the data sets. This one, Seaward, file number 266. When I read about it here, I find South Alaskan coastline earthquake prone. Well, 1966 to date, gorge sighted on Alaska Railroad Pier, but this seems to be a station that I should not include, and it's obviously not in line with the majority of other, because it's flat from 1960 up to 1990, and then sea level goes down, means land goes up, tectonic movements. So I will remove this one now. So I delete it from my file with selected stations. Like that. And then I also remove the file from the directory where I have the files stored. Like this. And now it will no longer be available to my program. This one also doesn't look okay. It is Pago Pago, file number 539. It's flat and it bends abruptly. Something like year 2000. And the place is American Samoa, in the middle of nowhere at Pacific Ocean. And of course the data is the data I have shown, and station documentation, and they don't say what is the problem, but there was a tsunami in the area in 2009. So I think this must be caused by movement on the Earth crust. This is not sea level change. So I remove this one also, 539. Here is another one that cannot be correct for global sea level. It is a slope like that, and then it bends and the sea sinks a lot. This is number 444, and I look it up. It's near Bangkok. Station name is where did I find it? Here. Fort Phrakshola Shom Klau. Anyway, it's the same curve, of course, and the information here data flagged suspect. It looks way out, and I don't know how to correct this. I just delete this file. Here is another one, Churchill, file number 447. It's in Canada, Hudson Bay somewhere, and the data here is the same as I have seen, of course, in my plot. And here, from 1950 up to 2010, this cannot be useful. This must be an artifact that I shouldn't include. This is Kushiro, file 518, and it doesn't look right at all. So I look at the station documentation, and it says a massive earthquake. This is in Japan, not too far from Fukushima. So I should delete this one also, file 518. Here is another station that has a behavior that is not compatible with the global sea level change. It's Yakutat, file 445. This is in United States. Well, Alaska. And I look at the text. Earthquake prone. The sea level appears to have an accelerating downward trend. And they have checked with close-spaced other stations. So, looking at the yearly mean, this is obviously something that I also should delete. Here is all the data on top of each other. The number of stations is 232, and the bright white is from 1960 up to 2021. The red line you have seen up to now is a slope of 2.4 millimeters per year. I have now made a change, starting from the first year up to 1930. I add 0.6 millimeters per year. And it steps every month, so I add 0.6 divided by 12 for each month. And then from 1930 to 1992 I make it 1.4, and after 1992 I add 3.4. That is according to the graph I showed early in this video. So T1 is what is incremented, and if month is a positive number, it means it is not a flagged data point. I will set a pixel to obtain the red line, and there is a scale factor 0.5, because I also have a 0.5 on the data files to make it fit the screen well. Here is the sea level again, and these are the lines that you can see here. It's 0.6, and the next one 1.4, and then 3.4 here, millimeters per year. And I can step through the files. This particular one, it looks very flat all the way. And here is something that looks more like the bending line. And it's obvious some noise reduction and processing of these files, and then an average of them will be necessary to judge what is a reasonable change of the slope around 1990, because that's the aim of what I'm looking at. Did it really change from 1.4 to 3.4 in year 1992? In the daily newspapers here in Sweden, and also, of course, on the internet, we can see sea level rise is happening now, and the rate at which it's rising is increasing every year. And of course, there is a worry that the increase will come and become very dramatic in the future. But I have a feeling that the statements saying that it is already increasing rapidly isn't quite in agreement with what we can see from the tide gorge measurements. And that's why I have tried to investigate this myself. And I will show a preliminary result first now. The white curve here is the average of something like 230 tidal gorge measurements, those that cover the range 1960 to 2020 and that don't have any obvious errors in them. I mean things like earthquake or measurement problems. The red line is Columbia.edu, the curve that I just recently showed. It shows an acceleration of 2 millimeters per year from here and then bending here. Then there is a study by Zoe Finn. He finds 1.3 millimeters per year as the change in slope from the 1960 to 1992 interval to the latest interval up to today. Here is the study by Zoe Finn, and it is much closer to what I have found than the other study, this one, which is from Columbia.edu. And there are many such diagrams on the internet. And if you continue to look at this video, you will see exactly how I have arrived at my preliminary result. And then I will analyze it a little bit more in detail to see if I can find good reasons why studies differ, or if I find some other interesting aspects of tidal gorge measurements. What you have seen up to now was recorded in May 2021. I did not continue making a video because I decided I don't want to publish this, because there is nothing new that I can present. About 1.2 millimeter was what I found. I have, however, continued, and now I realize that among the climate change skeptic people, many say that there is no sign of increase of the sea levels if you go for the tidal gorges. Here is one example, Hoek van Holland. If I pronounce it right, I don't know. There is a straight line, and you can clearly see that it doesn't bend at the end. Now, that is not really a good argument. You can look at the 50-year trends. They vary like this. And this variation is maybe not so significant, because actually with a 50-year trend there are too many points. So you have only this region. Each 50-year trend is the average over 50 years. So this minimum here is just 1 point, and this is another point, more or less. From here, 80 to 30, that is the 50-year. So this doesn't say anything, really. And this, well, it's so noisy, it doesn't say anything either. So I decided, after all, I will continue to make video showing what the evaluation I made is, and why I think I can make the conclusion that, yes, tidal gorges really show that the sea level rise has increased, although the uncertainty is fairly big. So here is what I see from the same station, Hoek van Holland. I have fitted a straight line, the white line from here to 1992, and this very noisy curve gives a small slope upwards under this time period, and from 1992 up to 2020 the slope is a little bit downwards. Now I have removed the average value and the linear trend, so that's why it is on the average the sea level shift is 0 over this time period. The yellow trace here is a line that is fitted from here to here, and which has one bending point at this point. So when the data is good, the white curve and the yellow curve would be close to the same place. Now the difference in slope is minus 1.14 millimeters per year based on the white lines, or based on the line that has one corner point, it is minus 1.25 millimeter per year. And of course the uncertainty is very large. And there are various measures of noise, 3.5 millimeter. So of course this doesn't show that the global sea level change is anything particular. But there are many stations, and I can press T here, and you can see how the trends are going up and down for the different stations. And the average of 232 stations is 1.3 millimeter per year, 1.22 millimeters per year based on the white lines, but 1.19 based on the yellow line. But the data, many of the files are not really good enough to be included here. So I have here some tools. This is the statistics. Misfit is how the white and yellow lines not fit to each other. Instability and instability divided by noise. Instability and instability over noise. And RMS, that's an RMS error, and that's a ratio between RMS errors, and this is the other RMS. So I can see some data points are far out from the normal behavior. So, for example, this one, there is one point here which is 10.0, and I can say that maybe I should set a limit at something like 4 here. So I change this to 4. And then I find a slightly different result. And I have now 223 out of the 232 stations. And then looking here, it looks like I have, these are a little bit outside, so I change from 4 to 3.5. And here, this ratio, there is one point that sticks out very much, and there is this tail that indicates that these are not so good. So I set the limit here to, let's say, 1.1. And this looks reasonable. And here I have a couple of points that are very far out. So I set this to maybe 40. And this has changed the difference. It is now 1.8, 1.87. And the number of files I have used now is only 46. So this wasn't a good idea. I will play a little bit with these numbers and see what seems more reasonable. I have set various limits here, as you can see, and these two graphs, they show the difference between the slopes, computed the two ways that I am doing the computation. And I don't set any limits on that, because this is what I want to evaluate. And you can see that it goes from a -3 to +6, regardless of the way it is computed. And if I look at the average, I have to expand the scale to see better. This is what I have. And the difference in the sea level rise is now 1.6 millimeters per year. Now I will show how data is processed by the program I've written. The problem is uncertain and missing data points. The uncertain ones are in magenta, and the real valid points are white, and missing points are missing. So I select points, then I type B, and you see the ones that are flagged as suspicious, I just set them 0. And the next step is to convert this to the input to a Fourier transform. That's here. I have removed the, let's call it the DC component, and the slope. So I have subtracted a trend line to get something that is flat and that has the average value 0. And when this goes into the Fourier transform, what comes out is this. Here is the yearly variation. This is half year. The variation over the year is not a sine wave. It is a little bit distorted. And here it has a component of 6 months. Then the next step is to remove what is not periodical. And that comes here. So this is the 1 year, half a year, a third year, a quarter of a year. And then I take the back transform of this. And this is what I see. And then you see the yellow lines is what I have interpolated. And then the next step is to replace all the points that are valid and retain those that are interpolated from this Fourier transform. So then I get this. And you see the red points, they are from the Fourier transform, and the blue is raw data. And then I take the Fourier transform of this. So here is the Fourier transform. Maybe hard to see. One interesting thing is what you can see here. If I magnify it, it becomes more clear. Here is low frequency noise, and the next step, when I clean for only the periodic function, that is here, you can see I remove that. I just keep the very slow, that is the slope of the curve essentially, and that should be about 0. So this is some very slow variation with time only. But here are the periodic things. And then the output of this comes here, and I go down like this. And then the next step, of course, is to take the Fourier transform of this one. That's n. And then I don't show all the steps. I'll just continue in the same way. Here. And then the next one. And the next one. So this is the final interpolation I have made for missing and uncertain data points. And after this I apply a low-pass filter. That is Q, and it looks like this. And fitting the lines, it looks like this. And as you can see, the white lines here fit pretty well to the yellow that is fitted as a continuous curve with the point where the slope changes. The difference between this slope and that slope is 2.9 millimeters per year. And, well, 3 millimeters per year. And of course, when I look at the raw data, it's not so easy to see that. But you can guess that it goes something like that. Interpolation is good, but extrapolation is not safe. So I will remove some of the files that extrapolate too far. Here, for example, this bending down may be false. It should rather go up like that, perhaps. So I will remove this file 728 Izvestia Zinc, and also some other files that are similar. Now I have removed the files that required extrapolation, so the number of files now is 186, and I have no limitation on noise or other things that look odd. So I will set some parameters here and see what happens to the difference between the slopes in the first and the second time interval. These diffs still go from -3 to +6, and the peak is somewhere here, and that is the 1.2 millimeter roughly. I have set all the parameters to eliminate the most noisy or unusual measurement series, and then I get this result. The difference between the sea level rise is then 1.6 millimeters per year. And here you can see what parameters I have set, and these distributions look reasonably good. Now I'm only using 98 of the data files now, and we can see there is a significant peak here on the differences between the two slopes in the two time windows, and the curve is fairly symmetric. And there are 186 files. I have removed about half of them by eliminating those that are noisy or have a stability. That means noise at very low frequencies. And I don't know so much what to say about this, more than that there is definitely on the averages, regardless of how I process data, I find that the average of a reasonable number of these sea level gorges show that the sea level is increasing from the 1960 to 1992 slope to the 1992 to 2020 slope by a little bit more than 1 millimeter. Maybe 1.3 or plus minus 0.3 or so, between 1 and 1.6. And the accuracy is, as you have seen, not good at all. I think by having GPS measurements on a reference point close to the sea level gorges, one could do a better study, and I think those things are being done, but not for long enough time yet. Anyway, taking the data of this kind as a sign there is no change in the sea level rise, that isn't really fair. In case you want to do your own experiments with these RLR files from PSMSL using the software that I have been using here, I will show how to download and install Linrad, X-Linrad, which is a program for software-defined radio that I have modified a little bit to do these computations for sea level measurements. So it is this place. And then I right-click here, Save Link As, and this is where I want to have it. Save. And here is that directory. And 30 megabytes. So the command now is to unpack this file. Like that, and it unpacks the RLR and the software. And then I descend into the new directory, which is called C. And here I have to type configure first, /. And here you may get instructions what to do to install if you don't have compilers and other stuff. And there is no support for one of the software radios that people could use normally, but that's nothing to worry about. And then issue the command make xlinrad64. And it takes some time. When compilation is complete, start the program by pressing xlinrad64. And then you have to select what screen to use, and that depends a little bit on how you have set up your Linux. I can say A here for plain X11. Enter. And then I can say N for newcomer. And screen size, I want it, let's say, for sizes and percent, in percent, N, and then maybe 80 by 80%. And here is the screen, sea level. So I press A, and here we are. And commands are down here. A, B, C, and so on. Do you really want to exit? Yes. So this is pretty easy to start. The code for processing sea levels is all of it in the module menu.z. So it starts here, and the bottom is 1780 lines, and some of it is not related to the sea level things. So it is 1600 lines of code that is relevant for the sea level programming.